Without further ado, I'd like to introduce you to Rodrigo.
Hello, everyone. As Michaela said, my name is Rodrigo Marques de Sá. I'm product manager for pressure independent valves for Americas. And today I'm going to present to you guys the Belimo Hydronic simulator. So the Belimo Hydronic simulator is a tool that we developed a few years ago, and it is still in development. And we're going to show how hard it is when you start to balance your system. Okay, so with that said, I'm gonna start the presentation, and before we get to the tool, I'm gonna present as well some problems what we have in our installations. Okay, so we know and we understand that around 40% of buildings' energy use is HVAC. So a lot of people in the past years said or say, and studies shows us that 40% of the buildings today, they consume, it's consumed based on the HVAC. So we can talk about fans, we can talk about chillers, we can talk about boilers, pumps, and cooling towers, and all this stuff. So pretty much all these things gonna consume 40% of the energy in your building today. We also have problems where the cold or hot sensations are at the same time in a building, in different parts in a building. So a lot of people complain about to be very cold or to be very hot in some offices or rooms in a hotel, for example, and that's a very big problem. So we know that these situations happen a lot, and that's one problem that we see happening in a building. We also know that problems can happen in the startup. So when you start your system, something can go wrong. So for example, I design everything perfect, but in the real life, when I go there and I turn on all my pumps and everything starts to run, I can see problems happening, like I'm starving on the my coils or my fan coils or chillers or things like that. So many problems I'm gonna get in the startup, and I have to fix that. That's gonna be based on some installations or some design that was not very predicted in the past or on the design phase. So we also see a lot of problems on the startup. We also know, or many studies show us, that 50% of buildings suffer from low delta T syndrome. So we know that the low delta T is a big problem nowadays. So you have, for example, my chiller water has a certain design temperature, and I have a certain design temperature to go back to my chiller, and this delta T is good for my system. In the real life, when I have everything running well, I can see that some of them, or some of my delta T in the installation, it's not very good as I designed. So that happens because sometimes, because the layout, or sometimes the pumps, or everything in the system can start to reduce my delta T. So let's say that I have designed a delta T of 12F, for example. And in the real life, we have a lot of situations that we can get a 6 delta T on that, which means that I'm not working on my best or my optimum point of the system, so my performance will be lower, and I can also have a lot of problems in my chiller, or for example compressors. I can damage that, and the life cycle or the lifetime of this device, they will be lower as well. So that's a problem that I'm gonna have when I have a low delta T in my system. So we can also talk about most buildings are oversized or not performing as supposed to. So we understand that in some situations on the design phase, some constant engineers, they specify or design some device or almost installation with a K factor, or let's say a safety factor. Okay, so we are talking about 20%, 30%. It really depends who's gonna design my building. But we know that in the real life, many buildings and many systems, they are oversized, especially because we have to design something to work as a fully or let's say 100% running all the time. And we know that partial loads, which means that I'm gonna have not all the time running 100% gonna happen all the time. So we have studies saying that 2% of my year, I'm gonna have my installation running 100%. So the rest gonna run on partial loads. So on these studies, also we can see that 40 to 70% of partial loads gonna be my, let's say my sweet spot. So most buildings gonna run between 40 and 7% of load. So which means that let's say I size for 100%, or let's say I use some K factor of 20% more, and now I'm fully oversized on all my devices. So I can talk about coils, I'm talking about pumps, pipes, everything, okay? Here today, we're gonna focus on the balancing hydronic systems. So a lot of people also know that it's a very big problem when I start to balancing my system. So depends what I have. It is a challenge to do that. So many commissionings, I'm not talking about commissioning here, but we are talking about balancing. So when you have to go in the field and plug it in a device in a PT port, for example, and get there the differential pressure, and with that value, calculate flow based on the known CV that you have from that device, it's a very hard to do that. Because you don't have only one valve or one device, you have many valves or devices around your installation. So when you have, for example, variable flow systems with a manual balancing valve, for example, you have a static device doing the balancing, and you have a dynamic system fluctuating or trying to get the required flow for each terminal unit, which is a very hard thing to do. And the problem is when I have to balance in a system, I have to balance that for 100% of my capacity for my load. And as I said, we have the buildings running between 40 and 70% most time in a year. So now we should go back there and rebalance everything, or every situation that change in the field, I should go back and rebalance my valves. So that's really hard to do. And to be honest, it's not possible to do with a device. Even if I have a very smart device, I can do that. That's why it's really important to understand why manual balancing valves are not suitable for dynamic hydronic systems. Okay, so today I'm gonna go on this point here for the balancing hydronic systems, and I'm gonna show you guys how bad it is when we have manual balancing valves. So that's why the tool was developed, and that's how I'm gonna show you how it is bad. So here we have the Belimo Hydronic simulator. So it's a very easy way to get to this tool. So we're gonna go to the belimo.us website. I'm gonna click on here, and it's gonna open my browser. So here on the Belimo website, I can easily go on solution. So the tool is based on there. So I'm gonna go solution, then I'm gonna go to resource, and I'm gonna click under tools. You're gonna be able to see the Belimo Hydronic simulator. So I'm gonna click on here. I'm gonna scroll down a little bit. As you can see, we have many different tools. So here we're gonna find the Belimo Hydronic simulator. So we released this tool last January, and since then we have getting a lot of feedbacks regarding the tool. So if you have any feedback on the tool, let us know, and it will be a pleasure to try to improve the tool. As I said in the beginning, we are improving the tool all the time. So it's not a fixed or a done tool. So we are always going to improve that. So as you can see here, we can click on this link and we're gonna open the tool. So I'm gonna download that and I'm gonna open here. So that's a very simple way to get. So here I have my tool open, and that's what I'm gonna face when I open the spreadsheet. So it's an Excel spreadsheet, and that's very simple to handle with. So here on the cover page, I'm gonna have on the Belimo Hydronic simulator, I'm gonna have the possibility to select the flow units that I'm gonna work with. So I can work with liters per hour, I can work with GPM, I can work with liters per second or cube meters per hour. So in our case today, I'm gonna work with GPM, okay? Also, I can select the flow that I'm gonna have on my coil. So in this tool, it's not like a modeling tool, it's only a simulator. So I cannot really, how can I say that, simulate a real installation. Like if you have a project and you want to enter some data here, it's not possible to do that. So it's just a simulator to show how things gonna work, but it's not based on the project, the customer project data. It's based in some generic numbers here that we have behind this tool, okay? So in this case, to make things simple and easy to understand, I'm gonna have all my terminal units with the same flow. So that's just to make things easy. We know that in the real life, things doesn't happen like that. So I have different flows across my building. I have different pressure drops. I have everything different. But here, I'm gonna make things very easy. And even in easy things, I cannot have that. So what I'm gonna have here is I'm gonna select my flow. So my flow gonna be, let's say 0.8. I can pick whatever I want here. So it's gonna be 0.8 GPM for all my terminal units. I also gonna have the select, I can also select my differential pressure here unit. So I'm gonna work in PSI. So just to be, to make sense since I'm working GPM as well. So once I select all these units and my flow, I'm gonna go to my second tab here. So on the second tab, that calls manual balancing valve tab. So here, I'm gonna have my simulator. So my simulator here, as you can see, I'm simulating a 4-floor building. So I have 4 floors here, and in each floor, I have 5 terminal units. Okay, so this big box here, this rectangle thing, it's my coil. Okay, so that's what I have here simulating. So here on my left side, I can see all my design settings. For example, the flow per coil. So I'm gonna have 0.8 GPM, which what I select in the previous tab. I'm gonna have the delta P unit, so PSI. As well, I can see pumping cost, just to be a reference here, as well pump head. So in this case, I'm gonna work with a VSD, so my variable speed drive, or VFD, variable frequency drive. I can have that as well here, so I can play with this going up or down. Here we have a sample, what is each box here and what it means. So here in this box, so it's gonna show my coil, as I said. So I have this 0.94, for example. So here, if I click on this information button, it's gonna open this box. So it says current flow in the coil. So here, 118%, so that's the percentage of flow that I'm gonna have in the coil. So it means that if I have 118, so I'm gonna have 18 more flow than I require or design. So my sweet spot here is 100%. Here as well, I can see the differential pressure across the manual balancing valve. So we're gonna have one manual balancing valve in each terminal unit. As well, I have manual balancing valves on the branch, and also I have my manual balancing valve on the riser. So I can see the differential pressure on that as well. I also have here turns. So turns means my turns in the manual balancing valve. So in this case, we're gonna have the maximum turns that I can get in this valve, it's gonna be 4. So every time that I see number 4 in turns, gonna means fully open, okay? So, and I can open or close, depends on the arrow here. So I can start to close or open that. Okay, so I also have my blue pipe and my red pipe, which means my supply and my return side. Okay, also I have this button here, open and close. So I can easily open or close a valve. I don't need to turn that. I can easily go open or close, depends what I want to, okay? As well, as you can see here, I have these 2 different buttons. So one that we call open valves fully. So pretty much we can reset the system. So if I click on this, I'm gonna go fully open in all my valves. Everything is now open and running 100%. So if something happened here and I close this guy or that guy or this one here, for example, and now I want to reset everything, I can click on this button and now everything is fully open to my initial position, okay? So everything is running 100%. So I can just click on this button and that's it. And I also have this balance system button. I'm gonna show you later how it's gonna work with that. So, okay, so based on the balancing part of that, on the problem that we were talking a little bit early, so balancing is a very big challenge here. So we know that it's really hard to balance a system. So a lot of people have different methods or different points of view. Where should we start? Should I start in the first manual balancing valve, in the first device or the first coil, or should I start in my critical zone? So where should I start to balancing a system when I have it? So a lot of people say, oh, I probably should start in the last one or my critical one. So here, let's assume that this guy here, my last one, because now I'm in the 4th floor, that's the 5th device here. So I'm gonna start on that. As well as we can see here, the differential pressure is my lowest differential pressure right here. Okay, so that's the most hard device or coil to get flow, okay? So here we can say, okay, so let's start on this guy. So I have my valve fully open, so number 4, fully open. And when I start to measure the flow there with the 2 PT ports in the real life, I'm gonna get the value of 0.72 GPM. So my design GPM was 0.8. Okay, so now what I'm gonna do if I have my valve fully open and I only have 0.72 GPM here, I really cannot do anything, right? So because it's already fully open, I don't have flow enough, which means that I can have some problem on my pump head, or a lot of people say that yes, you have to increase your pump head to get enough flow there. Or I can start to balance all my system here to try to create a certain pressure drop, and then I'm gonna have flow enough there. Because as we can see here in my riser on the main valve, I have 29% more water in my system. So my system now is running almost 30% overloaded. okay? So I have flow enough there. So why this guy here is starved? Because probably some other coils are getting this, you know, this amount of flow that should be here instead. So let's say that, okay, I'm gonna start on the first coil, which is the one probably, which is the one that I'm gonna get more flow because it's the closest to the pump, and you know, some people say that. Okay, that's fine. So what I'm gonna do here, I'm gonna go to this guy and I'm gonna start to close that. So I'm gonna start to close to get my 0.8 GPM. Okay, now I have 0.7999%. I'm good. I'm gonna go to the next one. So I'm gonna go to the next one and I'm gonna start to close this guy here. And now I have 0.82, so 2% more. I'm good. I'm gonna move to the next one. So then I'm gonna go all through these valves, trying to balancing that. And as you guys can see already, I'm changing flow when I'm closing one unique device. So one single device can change all the others device. So you can only you can see not only in this branch, but you can see in the entire building flows changing all around. So when I get to the last one, let's say I'm gonna go to my last one here in the first floor, and that's where I'm gonna get my 0.8 GPM. I'm good. And what's happening is, if I want to go back to the first one in this first floor, I'm gonna see that now I have 10% more flow here. In the second one, I have 12% more water here. So I did balance, but now I change all the adjustments here, and that turns everything here to be overflowed. So what's happening is, here I have a manual balancing valve for a dynamic system. That's the problem. And I can really have a smart device that's gonna calculate all my turns, gonna make everything green. And that's why we have this balance system button. So once I click here, I'm gonna have everything green. So everything is green. Now, everything was balanced. It took me like, I don't know, here to balance that, let's say an hour. In a real life, it took me like a few weeks or a month to have everything balanced. Everything now is running 100%, and the problem is when we have partial loads. So as I said, only 2% of the time in a year runs 100%. The rest gonna run between 40 to 70 or more than that. But let's say that we're gonna have partial loads most time of my year. So now what's happening is, okay, everything is good here. Let's say that the first floor, nobody's in this floor yet. So I'm gonna close this valve. So I can close this guy here. And now what's happening is all my other floors are overflowed. So let's say that this guy in the last floor, my fourth floor, they are not in this room. And this guy here is not here. And as well, this guy. Okay, so now I'm changing that. I'm just changing the manual balancing valve. I don't have any control valve here yet. And I can see that things are not working. So when I have control valves here, proportional valves, they are modulating all the time, and that's gonna be a really mess thing. So that's the problem. Now I have everything overflowed. So this guy here that was really good, a green, 100% running well. Now I have 26% more flow running through that coil, which means if I have a cold water here, I'm gonna have a cold place in my room. So that's really bad for comfort. Okay, so that's pretty much the tool, the goal of this tool, to show how bad it is when you have manual balancing valves. We also developed the tab here that we call pressure independent. So this tab here is to show that, for example, in some of the terminal units here, we install a pressure independent valve. So pressure independent valve, regardless the pressure fluctuations, they will keep your flow constant. So design. So here we can see these valves, which is our PIQCVs, or mechanical pressure independent valves. So here I have a mechanical pressure independent valve here as well. So what I can see here, let's go back and open everything and now make everything balanced. So everything is fully working fully 100%, sorry. And now let's close this guy here, for example, and now I'm gonna close this guy here as well, and I'm gonna close this and that. So now I'm gonna see that I have overflow in some of my valves, but on the valves that I have pressure independent valves, I still get my design flow 0.8, regardless the pressure fluctuations. So that's to show how better, or what is the best solution when you have dynamic systems. So the best solution here is to have pressure independent valves. Okay, so that's pretty much the goal of the tool. And of course, I'm pretty sure you're gonna have a lot of questions here, and I'm gonna jump back to the presentation just to try to finish that on time. So for pressure independent valves, so Belimo has a whole portfolio for that. So we do have the PIQ CVs, which are our mechanical pressure independent valves. So for that line, we have up to 3/4. So we have 1/2 inch and 3/4. It's for zone applications up to 9 GPM. We do have the ball valve technology, which means 0% leakage. So you're not wasting energy on that. Even when it's closed. We know that some other technologies, for example, globe valves, some kind of globe valve short stroke that we call, you can still have some leakage on that. And if you do some math in a year, you're gonna waste a lot of energy having this kind of valve. We do have non-fail safe or fail safe functionality here. So it's a super cap. So we do have some some capacitors doing when you have something fail in your installation. This valve gonna go normally close, fail close, or normally open, fail open. We can also adjust the flow in the field through these clip settings here. So you can select your flow, and you can also measure differential pressure here. Not flow, but you can measure differential pressure. For that mechanical style, if you have the differential pressure between 5 and 50 PSI, you're good, you're pressure independent. We do have the electronic pressure independent version that we call EPIVs. So size here we have up to 6 inch, which means 713 GPM. We have the same functionalities of the PIQ CVs. As well in here, we have the ultrasonic flow meter. So we have a true flow reading. It's not just a calculation, let's say that. We have also multiple control modes, so you can do position control as a pressure dependent if you want, but you can also do a flow control, which means a pressure independent valve. We can do digital communication, so BACnet, Modbus, MSTP, RTU, no IP for the EPIVs, and as well analog, 0 to 10, 2 to 10. We also have the glycol ability here, so you can we can glycol compensate. So regardless the concentration of glycol that you have in your fluid, we can compensate that and provide the right flow. So we don't need any K factor on that. And the last, we have our premium product here, which is the energy valve. So we have on the energy valve all the functionalities that we have on the EPIV, as well on the glycol ability. We can also monitor the glycol and send the feedback of the glycol concentration to you. As well, we have a BTU meter built-in, a web server, cloud connection. You can see all the data through the web server or through the cloud. On the energy valve, you have the digital communication, MSTP, RTU, or IP, so BACnet and Modbus. And as well, you can, we have an internal data log here, so you can have 13 months on the device, or you can have lifetime data if you connect to the cloud. As well, on the energy valve, you can have the functionality or the feature to have a delta T manager. So you're gonna control based on your delta T. As well, we also have some analysis tool that you can optimize your system, or we can suggest that if you connect to the cloud, so we can give some tips, what is the best way to go. So That's pretty much what I have for today. And with that said, now I open for questions. Thank you.
Thank you so much, Rodrigo. For those of you who do have questions, what you can do is open up the question box, type in your question. I will read them aloud, and Rodrigo will answer them as best as possible. We are a little bit limited for time today, so if we don't get to everyone's question, we will reach out to you at a later time. If you joined us partway through the webinar, this webinar is being recorded and will be posted to our Belimo YouTube page at a later time. We do have a handout that is available for you regarding pressure-independent valves. Rodrigo, are you ready for some questions?
Yes, I'm ready. Let's
Perfect.
go.
So the first question is, can you please touch on, again, why low delta T is such a problem?
So a low delta T is a problem because when you have a lower delta T coming back to your chiller, for example, you have designed your chiller to the best performance. So let's say that you design your chiller to a 12 degrees F. So if you're getting lower delta T on that, that means that you're not working the best performance of the device. That means that everything there gonna have some problem. And let's say if you're very low on the delta T, you can also damage some components on that. So let's say a compressor. If you get a very low delta T on your in your chiller, you can damage the compressor on that. So you have to replace all these parts. So the problem to have low delta T, it's not only like the performance, but also you're gonna affect the device that you have in your chiller, let's say that.
Okay, great. Next question, is the calculation behind the tool based on real data or just dummy data?
Okay, so all the data that is behind the tool is real data. So it's based on manual balancing valve data, CVs, and differential pressures and calculation of pipes, everything. So it's real data. It's only not like you can enter that. You cannot change this data. It's just like we did some scenario that you're gonna have a static or let's say a fixed data there working, but you cannot enter manually each CV or differential pressure or pressure loss on your pipe. You cannot do that, but it's real data on there.
Okay, we have time for one last question. Is this tool able to handle my project data and show me what will happen in my installation as a modeling tool?
So as I said, unfortunately, it's not a modeling tool, so you cannot enter your real values of your project and see what's gonna happen. It's just like you can select flow, and as I showed, you're gonna be fixed on that flows that we put on the cover page, and you're gonna see what's gonna happen. But it's not really like a modeling tool. It's just like a simulator tool, okay? So that's why you cannot use your own data in this tool. For that situation, you're gonna find a different tools in the market, but Belimo has not this tool for that. We do have some energy savings tools that you're gonna enter your real data from the pump or from some other things, and you're gonna calculate how much you're gonna save, but not in that tool, not in the Belimo Hydronic Simulator.
All right, well, thank you everyone for joining today's webinar. Rodrigo, thank you for that excellent presentation on our brand new balancing hydronic simulator. Our next webinar is going to be on the 27th of March, and it's going to be on replacement of competitive fire and smoke damper actuators, focusing on codes and technical retrofit details. Thank you all so much, and I hope everyone has a wonderful day.
Thank you, everyone.